So here's my full wave rectifier circuit. Right now I don't have my capacitor hooked up. So this is the bridge rectifier, right? We showed you how to check those. I need to put a lab on there too. So this guy here goes AC minus AC plus. So I'm using 1/2 of my 12.6 volt transformer, which gives me about 6.3 volts, right? And it's coming in from here. So this is going to the two ACs. And then I have the top of my resistor plugged into the plus. And then I got this jumper right here that's taking the minus over to the other side of my resistor. We're okay? Okay. Yeah. The capacitor's not hooked up yet. This is the minus of the capacitor going to the, I'm putting it across the resistor, so this is the minus of the resistor right here. And this is the minus of my capacitor going in there, and we're going to go across the resistor in a second. So this is what I got. On my oscilloscope, which is what we expected, right? The time between pulses, if we measure the frequency, should be, so I got it in 2.5 milliseconds per division. Let's try to give it a multiple. So there's 1 millisecond per division, and I'm sorry that it's jumping, guys. Let's see if we can get it a little better on our trigger. Let's see what we're set the trigger on. We're triggered on channel 2. We need to make sure we're triggered on channel 1, right? The rising edge, and we got it triggered on the edge trigger. Let's see if we can get one alternation. Okay, so that's 1 millisecond per division. 1, 2, 3, 4, 5, 6, 7, 8. And you can't see this, but it's 8.33 milliseconds, right? Everybody okay? Because it's a little low. Can y'all see that? So, yeah, because it's 120 hertz. So here's where it starts. 1, 2, 3, 4, 5, 6, 7, 8. Since I'm on ones, and each one of these would be worth 1, right? So it looks like it's about 1.2, but it's hard to tell. So when you measure time on an oscilloscope, it's an approximation because you're of the number of divisions you have to work with, right? That makes sense. So for this to be a 1, if this to be a 1, then that means each one of these would be worth 0.2, right? Because there's only 5 divisions. So that's 0.2, and it's crossing about in the center, so that's 8.3. Okay? Which is what we should expect for 120 hertz. Everybody okay? So this is 120 hertz. So in your formula, you could use I times time over C, but we figured out it would be easier just to use frequency. We just change it over. Are we okay? So what I've got here is I'm across my 6.3 volt center tap transformer. I'm just using 1/2 of it, so it's 6.3 volt transformer. And then I'm halfway rectifying it. And then we could do our average voltage, but we're okay, right? Okay. Now notice, this is very, very important. This is a big difference between what we measure on a meter and what we measure on the oscilloscope. So over here, when I look at channel 1, I've got this guy right here that says DC, but it don't say DC volts, it says DC coupling. Everybody understand that? And of course, people don't understand that. They think they got to put it on DC to measure DC, and they think they got to put it on AC to measure AC. That is not true on the oscilloscope. You can measure AC on DC coupling just as well as you can on AC. In fact, AC is going to average it out and make it look like AC even though it's DC. Right? You understand that? So that means if I come over here, this is definitely DC because there's 0 right there. If I come over here and put it on AC coupling, it's going to put a capacitor in series with it, and now it's no longer in the center. Okay, see that? So normally, 99.9% of the time, we put our scope on DC coupling. It'll measure anything. The only time we use AC coupling is if I want to block DC. Everybody understand that? So in this class, we're going to use it a lot. So when we get into transistor amplifiers, they're amplifying an AC signal, but it's riding on top of DC, right? You understand? So when I come over here now, and just to get a better feel of that, I'm going to take it off of DC coupling. So, and then I'm going to come over and put my capacitor across here. I got a 100 microfarad capacitor. And I'm going to put it across the diode. I mean across the resistor. Crotchet does. These leads are so thin it don't want to stick in the slot. Okay, now it turns into that stuff right there. Okay. Turns it into that stuff right there. I can make it trigger. I can move my trigger up there. But here's my 0 reference right here. So what you're looking at is you're looking at a signal riding on top of DC. And I want to measure that. What would it measure? My trigger change? No. I don't like it though. But I want to measure that. So how am I going to measure that? I want to get an accurate measurement of that V ripple peak speed. So what I'm going to do is I'm going to tell my scope to block the DC and only let the AC component pass through. So I'm going to come over here on my coupling and I'm going to go to AC coupling. Now notice what happens. It hovers around 0 now, right? Let's see that. Move our 0 back up to here. Now I can come over here and I can turn that thing down and I can measure that ripple peak. Where's my trigger at? There it is. And now I can trigger it. Is the DC gone? No, it's still there. It's just I told my scope to block the DC. So the only time you use AC coupling on an oscilloscope is if you want to block DC. You understand that? Okay. So it's not like a meter. A meter, if you're going to measure AC, you better put it on the AC scale. If you want to measure DC, you should have put it on the DC scale, right? But it's volts. This is not volts. This is coupling. This is how we couple the signal into the scope. I don't call it DC coupling. I call it direct coupling. So if we was to look at the schematic on the oscilloscope, and we've got a switch, but it's done electronically on this scope. What we would see is I come into my oscilloscope, and I would have this switch right here. One position is actually a 3-position switch. This is connected to common. Then we got one position that we bring it straight in. And then we got another position that's got a capacitor in series with it. So it'd probably be, it's hard for me to draw this guys to get everything lined up. So I'll move my little dots over here. And these two inputs are connected together out here. So this is the input to the scope. So this would be DC, which is direct coupled. And then is AC, which is capacitive coupled. And then what I do is I come over here and I select which one do I want to go into the input circuits of my oscilloscope. That makes sense? So if you take AC, you'll learn one of the features of an AC of a capacitor that blocks DC capacitor. So if I'm trying to that up at the top is direct coupled. It means you see exactly what's there. If you put it on DC, you see what's there, right? If you put it on ground, if you put it on common, it gives you the ability to set the zero reference of the scope. So over here, we're going to do it electronically. So when I bring up the channel, I can come over here, bring up the channel menu, right? You see that? And I could put it on ground. So now my scope should paint one picture across the center. So now I can see exactly where my 0 volt reference is at, right? You understand? If I put it on direct couple, it's going to show me what is there. So this is actually what's there. Well, what happened to my trace? It's way up here somewhere, right? You understand? Because I got my voltage turned down so low. But it's up here. Now we've got a signal riding on top of DC that I need to measure, but I can't measure it because it's showing me exactly what's there. So I need to tell my scope to do what? To block the DC component of that signal. So I come over here and I'll put my scope on wrong thing, Rich. DC coupled. I'm sorry, AC coupled, right? Which is technically capacitive coupled. And we get people. Now I can do what? Now I can come up here and I can turn this thing down and see, I can actually measure that ripple voltage. So here's the capacitor charging, this is the capacitor discharging. So what would my ripple voltage be? I got it on 200 millivolts peak to peak, 2, 4, 6, 8, right? That would be 1 volt, about 1.6 volts. About 1.6 volts. But it's real hard to measure when you're doing what? When you do DC couple or direct couple, it's hard to measure because when you start turning your oscilloscope down to get a good measurement, where does it go? It's gone off the screen, right? Understand? Now, sometimes you can shift your 0 reference down here since you're measuring DC. You can move it down there, but still, I still can't see it. But it's still not going to be what? It's still not going to be accurate enough for you to see it. Everybody understand that? Are you okay? So when do you use the AC coupling on a scope? When you're on what DC? If you don't want to block anything, you use the direct couple, right? You understand? And you actually see what's there. It measures AC just as good as it measures DC. It has no problem with it at all. And that's a big problem I have. I've had guys out there that knows electronics, and they'll come over there to my scope and says, "Oh, you need to put it on this. You're measuring AC, you got to put it on AC." I said, these guys, if it's your boss, you ignore him or her. If it's not your boss, you correct them, right? So scopes and meters are not the same. They are not the same. Everybody understand that? Like on a meter, what's the black lead on a meter? It's not common. It's meter common. It's not circuit common. It's meter common, which means what? You can put it anywhere in the circuit you want to. That's meter common. It's not common. It's meter common. If it was common, you couldn't probe inside a circuit because you'd be moving your circuit common inside the circuit, right? You understand? So it is not common. It's not circuit common. It's meter common. It's what your meter is measuring relative to, right? You understand? On a scope, this guy right here is ground, guy. This is not common. This guy right here is ground. So if I was going to say, okay, I'm going to come up here and I put that ground right there, what did I just do? I just shorted out that resistor. I just created a short circuit. because I try to put ground on both sides of my load, right? You understand? So once you establish a ground, if your circuit is referenced to ground, then you got to put your scope, you got to put it on ground. You cannot probe inside the circuit. Now there is a technique that you can do where you come in and you'll put your other meter on lead on the other side, right? You understand? And then what you do is you come up here and you tell your scope to do math. Let's figure out where to do it on this. So let's see. Oh, here's math right here. So I can multiply channel 2 times channel 1. I could do what? Oh, here's operation. So I could do what? See what I'm doing? I'm selecting what? Oh, I'm sorry. I need to say Richard up there. Oh, it was up there. So what you do is you don't put your ground, you put your 2 probes on what you want to measure across, right? You understand that? That makes sense? And then what you do is you come up here and tell your scope to subtract the 2 inputs, and that's going to be a difference in potential. So on this scope right here, I would select what? You'll see that? Math, right? And then once I select math, I would come up here on my operation and tell it to subtract, and it's going to subtract channel 1 from channel 2. So your scope is going to display the difference between the 2, and that's what a voltage drop is, right? It's a difference. But you can't probe the ground inside your circuit, right? You understand that? But you can use it like a meter. So this is using it like a meter, right? You understand that? But we tell our scope to do what? We use what? We use 2 probes, and then tell it to do what? Math. Tell it to subtract. Tell it to do math, and then tell it to subtract the 2 probes. And then now I could come in and I could probe inside this circuit, and I could put my leads anywhere I want to. So I could look at my AC input now, right? You understand? So I could come up here on AC here. Oops, gotta be real careful. And I could come over to AC here. And then I should be able to measure the AC signal. Don't like it. I am across it, right? But this is the way you would probe, right? You'll understand that. You could come in and do what? Now you can use a scope like a meter. But you can't probe your watt into the circuit. You can't, because ground, it's a ground. You're setting up the common for the scope, but the common on the scope is reference to ground, right? You can plug this into what they call an isolation transformer, and then you can move your common in there, but both your commons have to be on the same side, and everything that's got metal on it becomes electrically hot. So we had that out at US Steel, but you got to be really, really careful, because now your scope, all these things that are metal are now electrically got voltage on it, right? So, are we okay? Okay, guys, what lab was we working on? So we went in and made the corrections to the lab, right? And we're working on the ones for, what are we working on? 31. 31 we've already did, right? And then we'll go into 32. I told y'all the corrections y'all need to add, right? Anybody need to talk about anything on those?
Oh, yeah, you told us to add the extra box.
Yeah, they add extra boxes to calculate before we measure, right? Now, why are we doing that? Well, we're doing that so we can prove we understand how these circuits work. Right? You'll understand that. And then we added the capacitor And we wanted y'all to calculate V ripple peak peak. But here you're going to use V peak to get an approximate, V peak out to get the approximation on your current. Everybody okay there? Any questions? So our parts kit should be in there. And then the trainers should be in there too. But y'all's trainers got those names on, right? Okay, so everybody okay? Got any questions? We got two people that's at. No, we got two people that's at.